Generalizations of the Ramsey theorem. Example 13.8. Any two of the 17 people are corresponding with each other on one of three subjects. Prove that there are three among them so that any two of the three of them correspond with each other on the same subject. This example generalized example 13.1 in the hotel lobby in a major aspect. Now the relation between two people can be of not only two kinds, they either know each other or not, but of three kinds. So, if we represent our people by a K17, then we have to color the ages of this K17 by three colors. Solution of example 13.8. As we have just explained, we have to show that if we color each of the ages of a K17 either red, or blue or green, there will always be a triangle with monochromatic ages. Choose any vertex V of our K17. As V has degree 16, it follows by pigeonhole principle that there is a color so that at least 6 of the ages adjacent to V have the same color, say green. Let G be the set of the other endpoints of these green ages. If there is any green edges between two vertices of G, then we are done, as those two vertices of G and V span a green triangle. If not, then all the edges among the vertices of G are red or blue. However, G has at least 6 elements, so it follows from example 13.1 that the vertices of G span either a red triangle or a blue triangle. Theorem 13.6 can be generalized to more than two colors the following way. Theorem 13.9. Let n1, n2, n3 until nk be positive integers with k fixed. Then there exists a minimal positive integer n which is equals to r of n1, n2, n3 until nk, so that if n is greater than capital N, and we color all ages of G which is equals to kn with colors 1 to 3 until k, then there will always be at least one index I in k braces, so that G has a kni subgraph whose ages are all of color I. We only provide a sketch of the proof. After reading it, you should be able to see how to proceed in the general case. You can check your work by reading the solution of exercise 1. Proof of theorem 13.9. We proved the statement by induction on n1 plus, n2 plus, n3, and so on plus nk. The initial case of n1 equals to n2 equals to n3 and so on equals to nk equals to 1 is trivial. Now let us assume that we know the statement for all positive integers n1, n2, n3, and so on until nk, whose sum is less than m, and prove it for the case when the sum is m. Note that by our induction hypothesis, we know that the positive integer r of n1 minus 1, n2, n3, and so on until nk exists. Set n equals to k of r of n1 minus 1, n2, n3, and so on until nk, then minus 1 plus 2. Assume G has a vertex V so that the color that occurs most frequently among the edges adjacent to V is color 1. That means that at least R of n1 minus 1, n2, and so on until nk edges adjacent to that vertex are of color 1. Let S be the set of the endpoints of these edges other than V, and let Ks be the complete graph with vertex set S. By the definition of R of n1 minus 1, n2, n3, and so on to nk, either there exists an I in the set 2, 3, 4 until k, so that Ks has a Kn subgraph with all ages colored I, and we are done. Or Ks has a Kn1 minus 1 subgraph with all ages colored 1, and then we are done again, adding V to this subgraph. Another direction in which the Ramsey theorem can be generalized is that of hypergraphs or set systems. To make a long story short, in that generalization, we color not the ages of Kn, but the Kr subgraphs of Kn for some fixed R. The special case of r equals to 2 corresponds to the traditional situation, that is when the edges are colored. Then the following is true. Theorem 13.10. We color each kr subgraph of kn with one of the colors 1, 2, 3 until k. Let n1, n2, n3 until nk be positive integers. Then there exists a minimal positive integer n, which is equals to rr of n1, n2, n3 until nk, so that if n is greater than or equals to such a capital N, such the minimal positive integer, then there exists an index I which is in a k braces, so that kn contains a kni subgraph, whose kr subgraph are all colored I. The proof is omitted. It is conceptually not more difficult than that of Theorem 19.9, but it involves more notations. The following is a very surprising application of Theorem 13.10. So far, our studies in Ramsey theory did not involve any geometry at all. Still, we will be able to use our last theorem to prove a result of geometric nature. Theorem 13.11, the Erdős-Zacharias theorem. Let n be a positive integer. Then there exists a minimal positive integer es of n, so that if there are n which is greater than or equals to es of n points given in the plane, no three of which are collinear, then we can choose n points from them that form a convex angle. Before reading further, you should check your understanding of the definition of es of n by proving that es of 4 is equal to 5. Proof. We claim that R3 of n will always be such a positive integer, not necessarily the minimal one. Take the complete graph whose vertices are our R3 of n points in the plane. Color its triangles red or blue according to the following rule. Number the points from 1 to R3 of n, and color a triangle red if the path from the smallest number via the middle one to the largest one is clockwise. Color a triangle blue if that path is counterclockwise. As our graph has R3 of n vertices, there will be a kn subgraph with monochromatic triangles. We claim that the vertices of this kn subgraph form a convex angle. To see this, it suffices to show that there are no 4 vertices in this subgraph, so that one is within the triangle spanned by the other 3. In other words, we need to show that the configuration shown in figure 13.2 does not occur. Such a configuration cannot occur. Assume without the loss of a generality that A is less than B, less than C, and that all triangles of our K4 are at hand are red. Then the fact that triangle ADB is red forces D, which is less than A, less than B. Then, however, D is less than A, less than C. And the triangle DAC is blue, which is a contradiction. This completes the proof. We mentioned that there has been a series of improvements concerning the best known upper bound for es of n. The latest such result can be found in reference 39, where it is proved that es of n is less than or equals to 2n minus 5 choose n minus 2, then plus 1.